Welcome to sidza.com.
Bond dissociation enthalpy or the bond energy. It's the amount of energy that you require to break 1 mole of a particular type of the bonds. Suppose we have a chlorine molecule. The energy that you need to break the chlorine-chlorine bond here is what we call as a bond dissociation energy. And similarly, we have an O2 molecule. In that we have an the oxygen double bond, and to convert it O2 molecule into the atomic oxygen means you want to break 1 mole of the bonds between the 2 oxygen atoms. The energy requirement is 428. You can see from this data the bond dissociation enthalpy of oxygen is more than the bond dissociation energy of the chlorine. For the chlorine it is 242 kilojoules per mole. That means for chlorine, if you want to break a chlorine-chlorine bond, for 1 mole of these type of bonds you need 242 kilojoules. And for oxygen, if you want to break oxygen-oxygen double bond, for 1 mole of these type of bonds you need 428 kilojoules. So that's why it is 428 kilojoules per mole. This is a diatomic molecule, and you can just easily find out the bond dissociation energy of a diatomic molecule. However, in case of a polyatomic molecule, a molecule which contains more than 1 bonds, suppose we have a water and H2O. In the H2O, what will be the bond dissociation energy? The oxygen hydrogen bond. There are 2 oxygen hydrogen bonds. If you break 1 bond here in the water molecule, if you break 1 hydrogen oxygen bond, the energy requirement there is 502 kilojoules per mole. And then you want to convert the OH into hydrogen and oxygen. That means you want to break a 1 more oxygen hydrogen bond. Here the requirement is different than the first one, because the nature of the starting species is different. And here you need 427 kilojoules. So that means for a polyatomic molecule, in case of a polyatomic molecule, if you want to find out when we talk about the bond dissociation energy, it is basically the average. So we take it average of the two, 502 and 427 kilojoules divided by 2, that will be 464.5 kilojoules per mole. That means this is the average bond dissociation energy of the OH bond. Now when a chemical reaction occurs, we know in the reaction reactants, they convert into the products. And how a reaction takes place? Reaction, we all know that there is a bond breaking in the reactants and the bond formation in the products. So let's take here an example. If we have a hydrogen molecule, it reacts with the chlorine and it forms the hydrochloric acid, HCl. If you balance it, it will be 2 HCl. Now how much is the energy change? How much will be the enthalpy change of this reaction? That means if 1 mole of hydrogen reacts with 1 mole of chlorine, what will be the enthalpy of a reaction here? We can find the enthalpy of a reaction from the bond dissociation energy, or you can say the bond enthalpy, right? Because we know in a reaction there is a bond breaking that takes place in the reactants and bond formation that takes place when products are formed. So that means in this particular reaction you can find the enthalpy of a reaction from the bond dissociation energy of the hydrogen, chlorine and the hydrochloric acid. We know that bond breaking is endothermic step. So if you have to break the bonds here, you need energy that will be equal to the bond dissociation energy of the hydrogen. And similarly, you have to break the bond between the chlorine atoms. And after that, what's going to happen? Hydrogen and the chlorine, they will form the bonds. So you get 2 moles of the hydrochloric acid. And we know when a bond formation takes place, energy is released there, right? how much will be the energy release? Equal to the bond energy. That means the enthalpy of a reaction will be equal to the bond dissociation energy of the hydrogen plus the chlorine, and you subtract it now by the products, because bond breaking is endothermic step. You need energy here to break the bond, you need energy here to break the bond, and when products are formed, there is actually the bond formation, and when bond formation takes place, energy is released. So this step is exothermic. Now the total energy change of this reaction, you can find it from the bond dissociation energy of the reactants and the products. And how we calculate it? The formula is the enthalpy of a reaction will be equal to bond energy of all the reactants minus bond energy of all the products. Let me take here a couple of examples. We have a reaction between hydrogen and oxygen, it forms water. And here if you want to know what is the enthalpy of a reaction, in this case that means how much will be the energy change, whether it will be released or absorbed, is it endothermic or exothermic. You can find it from the bond energy of the hydrogen, oxygen and the water molecule, right? OH bond formation. So the bond energy here will be, the enthalpy of a reaction here will be equal to the bond energy of all the reactants, and the reactants are hydrogen and oxygen. We have 2 moles of hydrogen, so it will be the 2 times the bond energy of hydrogen is 436, because you have 2 hydrogen molecules, so that's why 2 times, plus the bond energy of the oxygen, which is 498. Now this is the bond energy of the reactants. I'll subtract it by the bond energy of all the products. See here in the water, 1 molecule of water, there are 2 oxygen hydrogen bonds. So for 2 moles it will be 4 times, right? There will be the 4 OH bonds, correct? So I'll write down the 4 times the bond strength, the bond energy of the oxygen hydrogen. So that is 464. Now when I calculate it, it comes out to be negative 486 kilojoules. This is the enthalpy of the reaction. This is the energy change that will be released, because it is the negative here, right? Negative means the reaction is exothermic. So that means the total energy that will be released here when 2 moles of hydrogen react with 1 mole of oxygen, the total enthalpy change is 486. So how much energy is released? 486 kilojoules of heat is released here in this reaction. Let's take another example here. In this case, we have a ethene molecule that reacts with the hydrogen and you get ethane. So what will be the enthalpy of a reaction here? Again, you can find it from the bond energy of all the reactants and the bond energy of all the products. Now here in this case, in the reactants, we have a carbon-carbon double bond. So I can write down here the enthalpy of a reaction will be equal to the bond energy of the reactants, and in the reactants you have a carbon-carbon double bond, 1 carbon-carbon double bond, and the bond energy is 612, plus there is there are 4 CH bonds, right? Carbon hydrogen bonds, 2 here, 2 here. So that means there are 4 carbon hydrogen bonds, and the carbon hydrogen bond strength is 413, plus there is a hydrogen bond, right? HH bond, the bond strength is 436. Now this is the bond energy of all the reactants in this reaction. I have to subtract it by the bond energy of all the products. And in the products we have a carbon-carbon single bond. The bond strength is 347 times, there are 6 carbon hydrogen bonds, right? 3 here, 3 here, so that means 6 times, this is plus 6 times the carbon hydrogen bond strength, so that is 413. Now when I simplify it, it comes out to be negative 125 kilojoules. That means the heat change here is minus 125 kilojoules. This is the energy released here again. Why? Because it is negative here. That means the process is exothermic, right? This is how we can find the bond, the energy of a reaction, enthalpy of a reaction from the bond energy values. Hope you got the concept. Thanks for watching the video. Bye for now.